Let me continue reading about all the awesome things that Aaron has.
We're 10 minutes into the list now.
That's right. Let me just finish this off. We're about 90% through. We also want to offer Peace Sloan Research Fellowship, NSF Career Award, multiple awards from industry. In addition to his work in academia, he also works at Amazon Web Services as one of the Amazon scholars. So without further ado, thank you, Aaron, for coming.
All right, thanks for having me. This is great. And I want to talk about a line of work I've been doing. This is with my colleagues Surbhi and my excellent students Ira, Natalie, Varun, and Myra. And I want to start by just sort of asking us to reflect on the nature of probability. So let me ask, like a couple of questions about probability. I mean, the easiest is something like, suppose I flip a fair coin 16 times. What is the probability that I get exactly 9 heads? This is something that, you could encounter in like a probability 101 class. There's different ways you could go about answering this question. We've got a really good mathematical model of things like this that happens to map extremely well onto the real world. So we could model a coin flip as a really random variable, and you could like compute the solution to this in closed form. And you get some number, right? And because it maps so well onto the real world, you could compare it to like what you would do if you physically conducted the experiment. I could just go and like flip coins for a long time and take averages. And that would also answer this question. And like fortuitously, we would get like roughly the same answer. That's what makes the mathematical model so nice. But not everything is like that. So you could ask like other questions in the language of probability. I could say, well, what is the probability that Mark Carney will be the next Prime Minister of Canada? And this is a question that people ask. You can go on to Polymarket. I did this a couple of days ago, and okay, the answer is 75%. But what does that mean? Like, of course, we don't have a mathematical model in which we can analyze such things the way we do for coin flips, and you can't conduct the experiment. Like, you can't repeat history, from now until the election over and over again. Maybe like if you posit a probabilistic model of the universe, it is at least philosophically coherent to believe that if you repeated this experiment over and over again, Mark Carney would be elected as the next prime minister like 75% of those times, but like, we don't have the ability to like conduct this experiment. And there are other things for which like the language of probability is maybe even like a little more tenuous. People try to use probability for example, giving confidence scores to the outputs of language models. So it's a figure from one of our own papers. Right, so suppose I ask ChatGPT, what's the leading cause of death globally in children under 5, and it says that it's diarrheal diseases. What is the probability that this is correct? Well, like this isn't even a question about the future. This is just like a factual question that I happen not to like know off the top of my head. But I could look it up on Wikipedia, and the answer would turn out to be that, this is either 100% correct or like 0% correct. Like it's unclear what it even means to say that, there's a 23% chance this is correct, and yet like somehow this is something that it seems like maybe would be useful. And so something that we often want, but for reasons related to these questions about probabilities can't get, is we imagine or pretend that there's a distribution, a joint distribution over feature label pairs. We've got features that we observe, the label is something we want to predict. And we imagine that there's this distribution, which is a convenient mathematical abstraction, but like, it's not clear that it's always a real object. And we see feature vectors, and then the thing we'd like to predict is the label. Maybe we just want to predict the label, or maybe the label informs like an action we want to take. Okay, if the label is like payoff relevant. And for many tasks, like given X, if I knew the true conditional distribution on Y given X, on the label given X, this would be a sufficient statistic for all sorts of downstream tasks. For example, I could optimize any utility function defined by my action and the label. But these probabilities are generally inaccessible, either because we don't really believe they exist. Like maybe the distribution is just a convenient abstraction to apply statistical tools, but maybe the probability of Y given X isn't even a real thing in any meaningful sense. Or even if we sort of buy into the premise that this distribution exists, if we're in a large feature space, we've probably not seen X more than once. And so we don't have, we typically have between 0 and 1 sample from this distribution. And so we can't estimate what this thing is, at least without making heroic parametric assumptions about what the real world looks like. Okay. So what can you do? Well, of course, you can make parametric assumptions and get guarantees that sort of go as far as you're willing to believe your assumptions. But the other thing you can try to do is you can try to sort of impose frequentist kind of constraints on your predictions that that hopefully have some meaningful semantics. And maybe the simplest one of these is called calibration. So suppose we do have a distribution over labeled examples. Maybe for now, assume the labels are binary. Calibration, which you may have heard of before, and we'll talk more about it in a moment, asks that the predictions be statistically unbiased, not just marginally, but conditionally on the predictions themselves. I want to be I like that my predictions are unbiased, conditional on the value I am predicting. So it is this sort of self-referential consistency condition. I'd like that the average of my predictions is equal to the average of the outcomes, conditional on what I'm predicting. So, on those days when I say there's a 20% chance of rain, it should rain 20% of the time. Now, the form of calibration is my predictor should be statistically unbiased, conditional on something. And calibration happens to choose that something as it's the value of my prediction. I should be statistically unbiased, conditional on the value of my prediction. But that's not the only thing we could condition on. I want to sort of think about maybe a family, hierarchy of things we could ask for from predictions that sort of correspond to guarantees of the form that my predictions should be statistically unbiased, conditional on some collection of events, where those events can depend on, well, they could depend on my own prediction, that's what calibration is, but they could also depend on external context in various ways. I could just have a general family of events, and I could ask that my predictions be statistically unbiased, not just marginally, but conditionally on these events. Okay, and there's no reason that I have to limit this to the one-dimensional binary setting, predicting whether it's going to rain or not. I could be predicting some d-dimensional, real-valued thing. I want the vector-valued prediction to be unbiased, conditional on these events. And so, I think a useful lens is that, the salient property of real probabilities is essentially that they are unbiased, subject to all possible conditioning events. So that's what makes probabilities probabilities. And all possible conditioning events is a lot of conditioning events. It's often more than we can guarantee. But you don't need them to be unbiased, subject to all possible conditioning events for many things that you might try to do. Okay, for when you actually sort of have some task in mind and then go and investigate like what you actually needed out of real probabilities, sometimes it's a weaker condition. And what I want to do in the rest of the talk is go through a case study of seeing when you can recover results that are true of real probabilities under weaker and tractable conditions. Yes.
Sorry, can you unpack this intuition a little bit more that real probabilities are outcomes every possible condition given?
Sure. So, like, I guess when you, and we'll talk about this a little bit more later in the talk, but suppose you are, a perfectly informed Bayesian. So there's a prior distribution from which examples actually are drawn, and given the observations in front of you, you form a correct posterior distribution. You can always imagine, without loss of generality, that the label, even if in reality it was drawn up front, is after you make your prediction resampled from the posterior distribution. And so you can think of what you're doing as a Bayesian as predicting before the label is sampled from the correct predictive distribution. And then when you go to compute your bias, because you've actually predicted according to the real probabilities from the sampling distribution, you have no bias. Okay. So this I think is like a very interesting general research agenda. Like, we can't get our hands on real probabilities for various reasons, but like oftentimes I think we don't need to, and what we really need when we drill down is something that we can sort of tractably enforce. And what I want to do for the rest of this talk is go through a case study of doing that. But I think this is sort of an exemplar of a broader research agenda. Okay, and let me tell you about the sequential prediction setting in which many of the results I'm going to talk about live in, that sort of is a setting that allows us to just avoid distributional assumptions at all. So we've got some context space X. Those are the features that are relevant for prediction. We've got some convex space in which our predictions live, like if there's D possible outcomes, maybe we're predicting probability distributions over those D outcomes. We're predicting things in the D-dimensional simplex. And then in rounds, what's going to happen is the learner will observe some context. The learner will, as a function of that context and the history, make a prediction. And only then will the actual outcome chosen by an adversary be realized. And one thing we could ask for in service of other goals is that our predictions should be such that in hindsight, when I look at the empirical distribution, there's no distribution up front in this setting, but in hindsight, there's some empirical joint distribution over predictions and outcomes. In hindsight, I'd like my predictions to be unbiased, subject to any collection of conditioning events that I specify upfront. I think this is a useful language, and the ability to do this will be sort of a key tool in what I am talking about today. And I don't want to talk too much about how you do it, but I want to use this result, so let me just tell it to you. Like you can do this for modest numbers of conditioning events. Okay, so there is an algorithm that will be specified by the collection of conditioning events that you care about. These events can be defined by anything at all that you know at the time of prediction. So any external context, any history, even your prediction itself. And the algorithm will promise that for arbitrary, D-dimensional adversarially chosen outcomes, the predictions you generate will have bias, conditional, not just marginally, but conditionally on these events, bounded by something like root T plus log of the number of conditioning events. Okay, the running time, however, will in general be linear in the number of conditioning events. So you can have a lot of conditioning events. The statistical cost is very low, but it might take a while to run. So you ideally don't have too many of them. Okay. So Okay, fine. So this was some statement in the abstract about, making predictions that are unbiased, subject to some number of conditioning events. Maybe this is some weakening of sort of true probabilities. I want to shift gears a little bit now and tell you a story to launch into a case study of what you can do with this kind of machinery. So I want you to think about, a world in which maybe some predictive medicine technology is used to inform medical decisions. Okay, so we've got a human doctor over here, and we've got some kind of predictive technology on the right. And what will happen is that patients will arrive. And these patients will have different kinds of data, different kinds of sort of observations that we can make about them. And some of these observations will be legible to both parties, both the machine and the doctor. Maybe these are sort of things that can be written unambiguously on the medical chart. So past diagnoses, blood type. But there might be some observations that are medically relevant about this patient that are legible only to the human doctor, not to the machine. For example, things that are hard to formalize, like, the patient seems a little bit grumpier today than previously, or maybe, the doctor has a sense of smell, and it's hard to encode smells for the machine. And similarly, of course, the machine has a ton of observations that are not legible to the doctor. It's been trained on millions of records, and the doctor can't read through those. And so, the machine might, oh my gosh, okay. The machine might make some prediction, but even if the machine is really good, even if we're in some future time where maybe the average performance of the machine learning model exceeds that of human doctors, on average, just the very fact that the human doctor has access to information that is not available to the machine means that sometimes the doctor ought not to follow the recommendation of the machine. It might disagree because of the other information the doctor has. Okay, so my student Natalie made these slides and is very proud of this transition where the doctor becomes sad at this moment. Right, so the doctor disagrees, and it's not totally clear what you do at this point. The doctor could make a judgment call and say, look, because of these qualitative observations I've made, I think the machine is wrong today, and I'm going to disregard it, and I'm going to follow my own sort of treatment plan. But better would be if, rather than just deciding to follow the recommendation of the machine learning model, or deciding not to and going your own way, there was a way to have a short interaction between the doctor and the machine learning model that didn't require sharing these features that each of them have that might be illegible to the other, but require only sharing things like predictions that would allow them to arrive at predictions and decisions that are strictly more accurate than either one could have obtained alone. Okay, that would be nice. Okay, now if you hear this story and you're a fan of early work on the foundations of common knowledge in economics, then this might remind you of Aumann's agreement theorem. So in case you're not, let me remind you about what Aumann's agreement theorem is. What it says is, if we have two Bayesians, perfect Bayesians, who truly have a correctly specified prior about the joint distribution on observations the doctor makes, observations the machine makes, and label. Could be a very complicated prior, of course, because the feature space is big. They have a correct uncommon prior, and they have common knowledge of each other's posterior distribution. What does common knowledge mean? Well, common knowledge is sort of the infinite limit of I know your posterior and you know my posterior, and I know that you know my posterior, and you know that I know your posterior, and I know that you know that I know, so on and so forth, in the infinite limit. Then we have to have the same posterior. Okay, so even though we didn't share observations, just having sufficiently deep knowledge of each other's beliefs means that we have to have the same beliefs. So basically because, if I know the prior, then knowledge about your beliefs gives me information about what your observations were, and I can integrate over all of those. And since I know that I know my prior, I know that you've done the same thing, and you can reason about this in the infinite limit. Okay, infinity is a long time. There's been some work since the original agreement theorem. In the early 80s, it was shown that actually, we don't have to have common knowledge of each other's beliefs. We could just have a really, really, really long conversation. I could tell you my posterior belief. You could update on that. You could tell me your posterior belief. I could update on that. The conversation might be long, but it's going to be finite. We'll eventually agree on a posterior belief. And in fact, Scott Aronson proved in 2005 that at least if we don't require perfect agreement, if we're okay with approximate agreement, meaning, let's say we're talking about just a one-dimensional quantity for now, we'll generalize this later, but if we're talking about just the probability that Carney wins the next election, that if we're okay with shaking hands and agreeing once our beliefs are within epsilon of one another, then with probability 1 minus delta over the draw of the instance from the prior, the length of our conversation will be at most 1 over epsilon squared delta before we reach epsilon agreement. Okay, the nice thing about this is that it is independent of the complexity of the distribution. We could have infinite dimensional observations, we could have a lot of them, there could be an arbitrary functional relationship between our joint observations and the label. None of that comes into the bound here. The length of the conversation we need to have is only, it only depends on the error parameters, mildly. And we never needed to share the observations. We only needed to have conversations about beliefs. And so it works even when our observations are mutually illegible. Okay. Of course, there are some drawbacks to this story that make it not a completely satisfying solution to the problem of human-machine interaction. Okay, so first of all, you can start complaining about every aspect of this story. So first of all, why do either of us have a correct prior at all, let alone a common one? The world is a complicated place. Where did we get this fully specified prior distribution over my observations, your observations, and the label? We probably don't have that. Even if we did have that, again, the world is a complicated place. So it is intractable to compute correct posteriors, conditioning even on our own observations. But these kinds of theorems are asking us to condition on something a lot more complicated, which is the conversation we've had. I have to be able to integrate over all of the observations you might have made that would have led to this prefix of a conversation transcript and update based on that. So that seems hard. It's unrealistic to assume of the human, and here you are in vector, even worse for you is you're on the hook to implement this thing. How are you going to do that? And of course, these theorems are about one-dimensional expectations, and often, generally the things we want to predict are not just one-dimensional expectations. There's probably 1,000 different diagnostic codes at the hospital, and the doctor's deciding between a number of different treatments. We'd like to be able to apply these theorems to richer prediction settings. And so what I want to ask is, can we, these Bayesian assumptions are really assumptions that everyone in this interaction is operating with real probabilities, correctly specified posterior distributions. Back to, pointing back to the beginning of the talk, in general, these things are hard to imagine getting our hands on. But can we recover the nice things about this theorem and maybe generalize them without making as strong an assumption? Can we strictly weaken the assumption. I want to make an assumption that is still satisfied by Bayesians, like just in case I'm interacting with a superintelligence or something, like I'd like to have my theorems hold, but like I'd like the assumptions to be satisfiable by someone who's not a superintelligence. I want computationally and statistically tractable assumptions that generalize Bayesian rationality, but that recover these kinds of theorems. And the answer is yes, and in this case, the solution is going to be to ask for things, ask that our predictions satisfy some calibration conditions, but not all of them. And we'll see that that's enough to recover these theorems. Yeah.
So slight question, is the goal here to like identify a hypothesis that is sort of the best hypothesis of the joint, let's say, set of observations, or is it to identify like actual like stereo distributions?
So as we'll go through, the setting I'm going to talk, the results will need it, although we will be able to lift these results back to the classical Bayesian setting and give new theorems in the classical Bayesian setting. The results I will talk about natively live in this like online adversarial setting in which there is no distribution. So yeah, posterior distributions don't even like exist in this setting to the extent that like it's what you said first, like we will think about our accuracy in the end by comparing it, by essentially giving regret bounds, by comparing it to how well you could have done in hindsight with some class of models that has access to the joint features, even though neither party did. Yeah.
So how does, I'm not familiar with the literature here and I'm not sure what the extensions are, but how do you think about the hardness results when there might be limited overlap in the distributional sense between what the human believes and what the AI believes?
Yeah, so we'll I think the answer to this question will become a little clearer as we go through the results. Since we're going to be working in an entirely worst case frequentist setting, like there's no notion of beliefs. Yeah. But like if everyone happens to be Bayesian, then we can get theorems in that setting. Okay. So what are we gonna prove? So first of all, I'm gonna introduce a new kind of conditional calibration. It's a calibration conditional on a particular thing that happens to be useful in this setting and it's computationally tractable. I'll tell you what it is, but for now, it's just called conversation calibration. And it is implied by correctly specified Bayesian rationality. So if you happen to believe that both parties in a conversation are, computationally unbounded, correctly specified Bayesians, then they will satisfy this condition among many others, and our theorems will apply. But you don't need to assume that because this weaker assumption is efficiently and computationally and statistically tractable, meaning even in adversarial settings where there are no distributions, we can give efficient algorithms that guarantee this, in a way that is only accuracy improving. And it's because of essentially this general thing I told you at the beginning, that we can always make predictions that are unbiased, subject to like polynomial numbers of conditioning events.
I check my intuition here, which is like, so, in the description of the theorem, you said, well, okay, as this conversation is unrolling, the Bayesians have to kind of condition on what they've seen, which is a conversation. And so like those will be the events somehow that you have to pay attention to. Now, like in Aumann's, you have these two agents from the same model. I'm kind of wondering what the analog for that is. Maybe it's already in the conversation calibration, because like calibration is going to kind of insist that like I'm at least paying attention to what the other person's saying, and I'm going to have to deliver conditions that are unbiased when the other person's saying things. And so I can't just kind of summarily ignore.
Exactly.
Right. Whereas like if I disagree with their model, like I could maybe summarily ignore what they're saying or something like that. Or...
That's right. It's like it's going to enforce that you don't ignore what they're saying, but like essentially the hard part would be to not ignore what they had said in the entire history from round one until now, because the number of length k conversations is exponential in k. What's going to turn out to be the case is you can forget everything except what they said yesterday. Like you only need to condition on what they said yesterday.
Yeah, interesting.
And conversation calibration will be enough to recover these, even quantitatively, the same fast convergence theorem, convergence and 1 over epsilon squared many steps to epsilon agreement in one-dimensional settings. In fact, like fast agreement is just a corollary of what you really show, which is that every step of the conversation substantially improves accuracy, and because the squared error can't go below 0, it's gotta converge quickly. And if you believe that the agents are Bayesian, because Bayesians are really well calibrated, in particular, they're conversation calibrated. All of our results lift back up into the Bayesian one-shot setting where there's not a sequence of conversations, there's just one, and we get guarantees, in expectation over a draw from the prior. And in fact, we generalize these results because we know how to do all sorts of interesting stuff with calibration. So we no longer need to talk about just one-dimensional predictions, we can talk about high-dimensional predictions, and a doctor who has some set of actions they can take, like treatments, and has utilities that depend on the actions and the outcome, and we can get fast agreement theorems in these settings. And like agreement is not the same thing as information aggregation. Like we could agree on something that is not as accurate as we would have obtained had we shared our features with one another, right? The simplest example is I see a uniformly random bit, you see a uniformly random bit, and the label we're trying to predict is the parity of those two things. If we shared the information, we'd be able to predict the label perfectly. But if I see my bit, I say, hey, I think that the probability the label is 1 is 50%. And you give me a high five, and you're like, I agree, it's 50%. and we've agreed really quickly, fast agreement, but we haven't learned anything. And so really we want more than agreement. We want to be able to promise, in certain settings at least, that the accuracy of the thing we agree on is competitive with the accuracy of the best model in some class that actually does have access to both features, both feature vectors, even though neither party in the conversation does, and we show how to do that as well. Not for parity, obviously, but for other classes. Okay. So what's calibration? So so suppose your favorite Canadian weather forecaster says, I'm identifying with the audience, says there's a 70% chance of rain tomorrow, as likely they have recently. How can you tell whether this is right or not? If it doesn't rain, were they wrong? Unclear. It's really hard to evaluate a single forecast. But of course, if every day they make a forecast, now you can at least start checking for consistency, right? You can't check if these are real probabilities, but you can check at least if they're self-consistent. You can falsify that they're real probabilities. One way is by checking calibration. How do you check calibration? Well, I can look at all of the days for which they predicted a 70% chance of rain. I can compute the empirical frequency of rain on that set of days, and if it's very far from 70%, that is evidence that they were systematically wrong. They were not predicting real probabilities. So of course, just because it was close to 70% doesn't mean in any way that what they were predicting were real probabilities, but at least you can falsify that they were. Okay, and I shouldn't check that just for 70%, I should check it for every other forecast they make. And when I look at 20%, I see, actually it was the empirical frequency of rain was substantially deviated from 20%, and so they were not calibrated. But if they pass all of these tests, if they're consistent with their own predictions on each of their level sets, then they're calibrated. Okay. So now let me tell you about how we're gonna embed this agreement story into a sequential adversarial setting. And I'm gonna describe for you a two-dimensional object. The columns of this object I'm gonna call days, and the rows of this object I'm gonna call rounds. Now every day, a new patient arrives, and now there are no distributions. So, the patients and the labels, these are chosen by an arbitrary adaptive process, an adversary. The patient arrives and has some features that are legible to the human being and some features that are legible to the model. Neither party sees both. And the person in the model now engage in a conversation over rounds. Okay, so at round 1, the person speaks and says, I think the risk is 20%. Then the model speaks, 40%, that's round 2. Okay, the person speaks, the model speaks, and at some point they get close enough together that we agree to call it a day. We shake hands. Okay. So then the next day a new patient arrives. And again, we have a conversation. Okay, the person speaks, the model speaks. Maybe we agree earlier. We don't necessarily agree on the same day. Okay. And this keeps going on every day. A new patient arrives, we have a conversation. And the conversation takes place over some number of rounds until agreement. At the end of every day, we learn the label. Okay. So days correspond to columns, patients. Rounds correspond to rows. So there is a sequence of predictions made at round 2. There is a sequence of predictions made at round 3. It's not the sequence of predictions made at round 3 doesn't include all of the days because some of the conversations ended before that, but it's the sequence of days for which conversation made it to round 3. Okay. Okay. So conversation calibration is going to ask that at every round, the predictions that you make be calibrated, not just marginally, but conditionally on what your counterparty said at the previous round. Okay, if they're saying things to decimal precision, if they're predicting a 0.7213964% chance of rain, we're going to bucket that just so that there aren't too many distinct predictions. Okay, so a Bayesian would be calibrated conditional on the whole conversation and the whole history. That would be too much. We couldn't do that tractably. I'm saying what you can do is you can essentially forget about everything other than the previous round and just make sure you're calibrated conditionally on what your interlocutor said at the previous round. And this is something you can do tractably because there's not that many conditioning events. Okay, so what do we do to check conversation calibration? We look at a particular round. We look at all of the days for which our interlocutor said something close to 0.1 at the previous round, if we're talking about the 0.1 bucket. We'll do this similarly for all of the other buckets. And we'll look at the sequence of predictions we made on those days, and we'll check that this sequence of predictions is calibrated. Okay, so the sequence of predictions we make at round K is now going to be partitioned into a bunch of subsequences depending on what our counterparty said at the previous round. And I want that the predictions should be calibrated on all of those subsequences. There's not that many different subsequences since we're only conditioning on what was said at the previous round, and so it's not hard to do. Okay. And the claim is that this condition alone, as long as both parties satisfy this conversation calibration condition, is enough to recover fast agreement at the Aronson rates. That's sort of 1/epsilon². And let's think about I'm not going to go through the whole proof, but I think the intuition is that hard. Let's think about the predictions at a particular round K. Okay, and now let's think about the predictions at the following round, K plus 1. And think about 2 cases, what could happen. Well, in case 1, on most of the days, we end an agreement. We predict basically the same thing as our counterparty predicted the previous day. This is a good case for us if we're trying to argue for fast agreement. We can't have too many rounds like this in which the fraction of days we agree is cut in half. In case 2, of course, the only other case is that quite frequently the conversation didn't end at agreement at round K plus 1, which means that the thing we said at round K plus 1 was substantially different by more than epsilon compared to what was said at round K. And like one thing, if you think about it, you can notice is that if I have to be calibrated to the label conditional on what you said, the only way I can substantially disagree with what you said is by being substantially more accurate. How come? Well, I'm conditioning on what you said and calibration conditions on what I said. So we're looking at subsequences of days for when you predicted, 20% chance of rain, and I predicted 30% chance of rain. And I'm unbiased on the subsequence, which means that it rained 30% of the time. But I was predicting 0.3, which was right, and you were predicting 0.2, and squared error is a proper squaring rule. So I have substantially lower squared error. And so, in fact, like, at every round for which there are a delta fraction of days that remain that haven't ended in agreement yet, if we don't epsilon agree at those rounds, the squared error of the predictions between these adjacent rounds goes down by epsilon squared delta. To do a simple calculation, but it does. And really, that's what you want, but like, yeah, you want that the conversation should be useful, that we should get more accurate. But a corollary of that, of course, is that we have to agree quickly, because the total number of rounds we can disagree is going to be at most the squared error of the initial predictions over the decrease per round, because squared error can never become negative. And so what you get is agreement after 1 over epsilon squared delta many rounds, minus some term that reflects the fact that you're never going to get perfect calibration. You're going to have some finite calibration error, but this term will go to 0 as at a polynomial rate, as the number of interactions gets large. Okay. So we get fast agreement, and as this term goes to 0, as it will for Bayesian, it'll be exactly 0. You recover exactly the 1 over epsilon squared delta bound that Aronson proved in the agreement setting, that in Aumann's agreement theorem, but without making any distributional assumptions and with only computationally tractable conditions. Okay. Now, as we mentioned, agreement is accuracy improving. Like, these conversations are accuracy improving. Things can't get worse by having this conversation with the model. But we don't promise, strict accuracy improvement. Like this parity example shows that, what we show is that the conversations can't go on for too long. And error decreases kind of linearly with the number of rounds of conversation. But we don't rule out that the conversations all end at round 1 and don't aggregate the information. This is what happens in the parity example. So if we want to promise something stronger than just agreement, and we want to say, for example, the final predictions are as accurate as the best function in hindsight in some class that has access to the joint feature space, we need a stronger condition. We can't just ask for conversation calibration, because conversation calibration doesn't make any reference to the features. I could satisfy this condition without looking at the features. But I can ask for forms of calibration that condition on other stuff, including the features. And in particular, I could ask for something that I'll call conversation multi-calibration with respect to some hypothesis class defined only on my features. Okay, so I could take, for example, the set of all linear functions on my feature space. And I could ask that my predictions be unbiased, conditional on the value of my prediction, it's calibration, the value of your prediction at the previous round, that's conversation calibration, and conditional on the prediction that any function in my class would have made. That's what makes it multi-calibration. Okay, and even if there's continuously many functions in my class, it turns out that this is no harder than solving squared error regression problems over the class. You can do this efficiently whenever you can solve learning problems. And so, for example, you can do it for the set of linear functions. Now, I can only do this with respect to functions I can evaluate, so it's only functions on my own feature set. But you can do it with respect to functions you can evaluate. Your predictions can be conversation multi-calibrated with respect to a class of functions on your feature set. Okay. It turns out that multi-calibration with respect to some class of functions is very closely related to asking for swap regret for some class of functions, just in case that word is helpful. Like if you've heard of swap regret but not multi-calibration, they're very, very similar. Okay, now,
Quick, minor question. What you're calling conditional calibration is also an example formally of multi-calibration, right? Or
yeah, usually when people say multi-calibration, they mean conditioning on things that are defined on the features, whereas here I'm conditioning on something external. But yeah, like you could define multi-calibration expansively enough to mean conditioning on anything. Here I just mean I'm conditioning also on some property of the features. Okay, so conversation multi-calibration is only stronger than conversation calibration. Oops, no, good enough. And so the agreement theorem still apply. Okay, so if I'm conversation multi-calibrated with respect to some class of functions on my feature space, and your conversation multi-calibrated with respect to some class of functions on your feature space, we're conversation calibrated, and so the theorem I just showed you applies, and so we quickly converge to a sequence of predictions we agree upon. But we agree on these predictions, and my predictions are multi-calibrated with respect to my function class, and your predictions are multi-calibrated with respect to your function class. And so the sequence we agree on is multi-calibrated with respect to both of these function classes simultaneously. Now, that doesn't yet tell us the kind of thing we want, because I want to offer guarantees with respect to some class of functions defined on our joint feature space. Whereas all we've gotten so far is that we're maybe simultaneously multi-calibrated with respect to a class of functions defined only on mine and a class defined only on yours. But it turns out that sometimes having a no swap regret guarantee with respect to a class of functions defined on my feature space and simultaneously a class of functions defined on your feature space implies an accuracy guarantee with respect to a richer class defined on our joint feature space. In particular, it does so exactly when the following weak learning condition is satisfied. This weak learning condition characterizes when swap regret has this boosting property. And it says, look, we'll say that my function class and your function class jointly satisfy this weak learning condition with respect to some joint function class. If for every distribution, if whenever learning over the joint function class is able to come up with a predictor that has better squared error than the best constant predictor, then it's got to be the case that either learning over my function class alone or learning over your function class alone can also improve on the best constant predictor. Maybe not by as much, just by a little bit, but if there's some way to improve on trivial predictions with the joint class, there should be some way to improve by less using predictions from either my class or your class. And so the general theorem is that, well, if we have the boosting theorem is if we have a sequence of predictions that are multi-calibrated with respect to my class and your class, and they satisfy this weak learning condition with respect to some joint class, then actually the predictions that we make are as accurate as the best predictions you could have made, even in hindsight, with this joint class. The joint class has access to both feature sets simultaneously. And of course, like we're able to reach a sequence of such predictions just through this agreement protocol where neither of us had access to the joint feature space. And there are actually functions that there are classes of functions that satisfy this weak learning condition. In particular, the simplest is just the set of linear functions on my feature space, linear functions on your feature space, and linear functions on the joint feature space. That satisfies this weak learning condition. And more generally, any hypothesis class that is bounded and star-shaped, that just means closed under downward scalings. Any such class for me and any such class for you satisfies the weak learning condition relative to the joint class, which is defined as their Minkowski sum. Okay. So a corollary is that Alice and Bob can engage in this conversation protocol. They never need to share their own features, and they're guaranteed that for every sequence, no distributional assumptions needed, to converge to predictions that are always as accurate as the best linear function on their joint feature space. Okay, I only have 1 minute left, so let me, rather than showing you all these pictures, just tell you one of the upshots. So, you know, the original Aumann's agreement theorem was this one-shot thing. Like we made all of these assumptions, you know, everyone's perfect Bayesian, there's a prior, but like it wasn't about averages over a sequence of patients. It was about like a conversation about like a single patient. But it turns out that all of these theorems, if you would like to believe that you know, the interlocutors are perfect Bayesians and, you know, working with the correctly specified prior, lift up to that setting exactly. And the reason is because Bayesians satisfy all of these calibration conditions, right? These are just relaxations of Bayesian rationality. And so you can imagine, just as a thought experiment, that these two Bayesians interact over an infinitely long sequence of patients, drawing each one IID from the prior. And the empirical calibration error of these Bayesians will go to 0. So when you apply our theorems to this thought experiment, this error term that is like this calibration error term goes away, because in the infinite limits, there is no calibration error. But also, since the examples were IID, Bayesian updaters wouldn't have needed to condition on anything other than the current day. And so the conversations are actually permutation invariants. The conversations are IID. And so this guarantee actually holds for the first conversation. And so you wouldn't have needed to actually conduct these infinitely many conversations. It holds in the one-shot setting. Okay, so this lets you recover old theorems. It lets you get new information aggregation theorems, right? So previous information aggregation theorems said, okay, here are conditions on the prior distribution such that perfect Bayesians will arrive at the Bayes optimal predictor as if they had shared their information. That sort of corresponded to assuming conditions that are somewhat stronger than our weak learning assumption on like the class of Bayes optimal predictors. But now, since we can lift all these theorems back, we get sort of agnostic versions of those. We can say, look, don't make any assumptions on the prior distribution. Perfect Bayesians, no matter what, will always agree. If they agree, they will always agree on things that are as accurate, for example, as the best linear function on their joint feature space.
I'd be surprised you wouldn't need at least like a positivity requirement on the prior, or do you mean that when you say arbitrary?
Well, let me. It's a dangerous question coming from you. So what do you mean a positivity?
Well, I mean, like if one of the Bayesians, or do they share the same prior still?
They have the same prior, yeah.
Okay, never mind.
Yeah, you could probably extend it somewhat beyond that, but we haven't. Okay, and then finally, like, you know, all of this talk so far has been about like one-dimensional expectations, but we know how to do fancier kinds of calibration. In particular, there's something we can do called decision calibration that is tractable even in high-dimensional settings. We don't condition on. So now, like, suppose the hospital has like 1,000 different diagnostic codes, and so nominally the thing we would be predicting is like a distribution over like 1,000 objects. First, like full calibration in that setting would be too hard, and second, we don't want to engage the doctor in a conversation about like 1,000-dimensional vectors. But suppose like what is relevant about the prediction is useful only insofar as it informs downstream action. So suppose there's like a certain number of like actions the doctor can take, treatments. And they've got a utility function that specifies the, you know, how good a treatment is given the actual diagnosis. We can have a conversation entirely about treatments now, entirely about actions. I don't have to talk about the 1,000-dimensional distribution over diagnostic codes. We can say things like, I think that, you know, given the distribution over outcomes, the right thing to do is to amputate the left arm. And the doctor can say, no, I think we should amputate the right arm. Right? The theorems say, we'll quickly agree to something, you know, like prescribe ibuprofen. And then we can, like again, we can talk about accuracy improvement in terms of utility. In fact, convergence is even faster now. There's no dependence at all on the dimension, and we can give these same kinds of regret bounds. All right, so now I've talked, I think, for 3 minutes beyond what I should have. So just to wrap up, what do I want you to remember from the talk? So real probabilities, things that you'd get from like correctly specified Bayesian posteriors. Like, in some sense, what is useful about these is they are unbiased, subject to all possible conditioning events. But for many purposes, we don't need that. And if it turns out you only need like polynomial number of conditioning events to recover the kinds of theorems you wanted from Bayesians, well, that you can do tractably with small amounts of data and then small amounts of computation. And what I went through here with the agreement work, this was one case study in this sort of broader research agenda, but there's other things you can do. So this is useful in statistical estimation. We can talk about estimating means and variances and quantiles with conditional guarantees. We can talk about uncertainty estimation of various sorts, conformal prediction that has conditional guarantees, not just marginal guarantees. We can talk about causal inference. We can talk about mechanism design problems, so they're replacing common prior and Bayesian assumptions in principal agent problems. And I expect there's a lot more. So I encourage you to look this stuff up. The stuff that I talked about today is sort of contained in 3 papers that you can find on my website. But actually, I should have put this up here. Like, if you're interested in learning about this stuff more generally, I have a rather extensive set of lecture notes. You can go to uncertaintyclass.com and find quite a lot of reading material about this. So thank you.
Yeah, fascinating. So let's take a question or two, and then we'll let you guys get some food, and then we can swarm Aaron with more questions if you have them. So any questions up there? Yeah.
Motivation. If you motivated this by thinking about like human and the AI agree, like converging to an agreeable prediction, but I think that it maybe requires some assumptions of consistency on the part of the human that humans often don't have.
Yes.
Do you have a sense of do you imagine this potentially applicable to two models held by different organizations or
Yeah.
do you have ideas of how to operationalize human predictions to make them fit into your model?
Great questions. So the first thing I would say, so yes, the form of our theorems is that if the predictions satisfy this property, then we get this outcome. And of course, the conditions are important to the theorems, and people might not satisfy them. The first thing I would say is that we were intentionally looking for predictions that were sort of strictly weaker than Bayesian rationality. So these aren't arbitrary conditions. These are conditions that would have been satisfied, if you were happy sort of modeling people as Bayesians. So of course, they still might not be satisfied, but they're a lot weaker than that. The next thing I would say is, it's possible to calibrate, I can build a megaphone essentially, such that you speak probabilities into one side of the megaphone. Probabilities are output on the other side of the megaphone. And the probabilities that are output are guaranteed to be calibrated. And also on any sequence, if I evaluate the squared error of the output probabilities, it's only lower than the input probabilities. So you can calibrate, it may not be that the doctor may not want to use this megaphone, but it is possible to produce such an object. And then your third question is a good one. There are other motivations for doing this kind of thing, but the two parties don't have to be a human and a machine, right? These could be any two parties that for whatever reason cannot share their features, right? There's one solution, of course, which is just aggregate the features and learn on the joint feature space. But whenever there's a scenario where you cannot do that, this is applicable. So one such scenario is if you're in a regulated industry like healthcare, there might just be sort of legal obstacles to sort of shipping patient data back and forth. Another example is it's just multimodal learning. Maybe like I'm, it's like a hospital trying to collaborate with like, a chain of physician offices, and one of them has vision data, like CT scans, another has transcripts of doctor notes, so text data, and they don't have like a big machine learning team. So like one of them might have a pipeline that's sort of geared up for learning on data from one modality. Another one might have a pipeline that's geared up for learning from data on another modality, and they just don't have the sort of human capital to like build a new pipeline that can do multimodal learning. And these algorithms are reductions from multimodal to unimodal learning. You only ever need to learn on your own data to run these protocols.
So I have a little bit of background in like non-Bayesian social learning,
Okay.
which is also interested in the question of like, suppose I have a group of agents or like whatever, some data and I'm interested in learning, let's say, what is like the maximum likelihood hypothesis that fits the joint observed data, maybe in this case features. And so there you can typically exchange beliefs over like hypothesis class, like over hypotheses. It's not clear to me here what is being exchanged and what's the relationship between these two approaches, I guess, of information aggregation.
Yeah, let's see. So I don't know exactly which literature you're referring to, but let me say two things and see if either of those address the question. So like, there is a literature that sort of models people as Bayesians, and this is recovering the same kinds of theorems in that literature, but under much weaker computational assumptions. It's hard to be Bayesian. It's not hard to do this. There's another literature that says, well, it's hard to be Bayesian, so let me take some just behavioral assumption. I will assume that what people do is just average the beliefs of their neighbors, and I'm just going to iterate this operation, and we'll just study this new operation. And that's tractable, but like, I would say it's sort of much less, it's a much less canonical like behavioral assumption in that it's not something Bayesians would do. So like, maybe people do it, but maybe not. The nice thing, I think, about the kinds of assumptions we're making is not only are they tractable, but Bayesians would do them too. So like, in general, to the extent that I want to make assumptions about people, I want them to be as robust as possible, because if the assumptions are broken, then the theorems won't hold. And so this kind of thing is sort of, is satisfied by like, really well-informed, really smart people who are approximating Bayesian inference. It's also satisfied by much weaker kinds of computational agents. And I don't care where in the hierarchy my interlocutor is living, like the theorems apply to all.
I guess this is maybe a clarification, which is like, what is being exchanged exactly? Like,
just predictions.
So, but is it like just binary, like unit-dimensional, like probabilities of like, this is my probability?
So, yeah, so in the simplest setting I talked about, where we're talking about like a one-dimensional expectation, it's just probabilities. Like, I predict 73% chance of rain tomorrow. In the sort of setting I mentioned at the end, which I didn't really talk about much, what is being exchanged is actions. It's like internally I have some representation of, maybe a beliefs on, distribution over 1,000 possible outcomes. Those beliefs, I'm assuming, will satisfy some small number of unbiasedness conditions, but like not too many. But what I'm communicating to you is not that vector, but the action that I think you should take. What is the best response action to my belief?
Okay, so there you would have like a finite set of possible actions, and you're trying to find which action would be optimal under the.
Exactly. I have 10 actions. I have, this 1,000-dimensional distribution. I'm computing which of the 10 actions maximizes expected utility under this distribution.
The last one.
Thanks for the very nice talk. It seems like every day you kind of get the perfect like label information, right? And a lot of like in the medical scenario that you propose, I assume that a lot of the actions that you would take would actually be getting more information by ordering new tests, right?
Mm-hmm.
This like do you have any hope for like more complex actions that actually inform what informations you get, kind of like
Yeah.
similar like convergence results for something like that?
So that's a good question. Okay, so the short answer I think is no, I don't have too much to say about that. But the longer answer is these theorems do not actually depend on observing the label at the end of every day. What they depend on is the calibration condition. Now, if the sequence being chosen is being chosen by like an adaptive adversary, the only way you can hope to maintain these calibration conditions in the worst case is if you do observe the label every day. But if things are not chosen by an adaptive adversary and you are reasonably well informed about the distribution, you can be calibrated without observing the label every day. That's what would happen with the Bayesian, right? So like all you need is the calibration, not that you observe the label every day. The other thing I would say is that I described for you the versions that work in this online adversarial setting, because in some sense that's the most general. But you can do all of this stuff also in the standard like batch setting, where there's a distribution. You don't start out knowing what it is, but there is a distribution. You have a training set of labeled examples, drawn IID from this distribution, but then at test time, you never see the labels. You just engage in a conversation about examples drawn IID from the same distribution your training set was on, and then the theorem solved. So, okay, so for the first part of the question, you know, nothing here actually crucially depends on observing the label every day. For the second part of the question, that's a great question, and I haven't thought about it much. Right? So you asked, you know, maybe the actions, maybe I can take actions like ordering tests that for which I don't have direct utility. You know, this isn't like the final thing I'm going to do. It's some costly action I could take to gain more information. I think it would be really interesting to think about how you should approach such settings, both if you're a Bayesian and, you know, under these relaxations. I haven't thought about it very much.
All right. Sounds like there's more questions, but we're gonna move to the next phase, which is eating. And you're welcome to grab some food and then find Aaron again. So let's thank Aaron.